Have you ever gotten a new computer and thought to yourself, this isn't really that much faster than my old one? Well, you're not imagining things. There is a really fascinating reason for that. So let's dive into the story of how our computers literally hit a wall and how a complete shift in thinking, from solo sprinters to massive teams, saved the future of technology.
First up, we need to understand the problem. Because for decades, we were living in this golden age of speed. But then, right around the mid-2000s, that whole era just came to a sudden, screeching halt.
It's a feeling a lot of us have had, right? You upgrade, you're expecting this huge leap in performance, but what you get feels more like a small hop. This isn't just in your head, it's a fundamental change in how computers are actually being built.
Now, just look at this chart. The story it tells is so clear. You can see the clock speed, that's basically how many calculations a processor can do per second, just climbing this incredible steep curve for over 30 years. And then, flatline. The party was over. And to put some numbers on that, we went from performance pretty much doubling every 18 months to something way slower. I mean, a 50% yearly improvement is just staggering. 20%, well, it's nice, but it's a completely different world. So what on earth happened?
Well, the culprit was physics. As this incredible chart shows, making processors faster meant cramming more and more power into a tiny space, and that generates a ridiculous amount of heat. They got so hot that the power density was literally on track to match a nuclear reactor. Chips were in actual danger of melting themselves.
Okay, so if we couldn't make a single processor any faster, you might be thinking, why not just accept that things are fast enough? Well, because the world's biggest problems demand computational power that we can barely even imagine.
And that's a fair question. For our day-to-day tasks, most modern computers are fantastic. But our ambitions as a species go way beyond just sending emails. We're trying to solve some absolutely monumental challenges.
Things like accurately modeling climate change, or discovering life-saving drugs, or sifting through the mountains of data from the Large Hadron Collider. All of that requires computation on a scale that makes our laptops look like pocket calculators. These grand challenges were seriously threatened by that speed slowdown.
And this is where the story gets really good. This is the solution. When one person can't run any faster, you don't try to make them faster. You build a team. And in the world of computing, this idea is called parallel computing, and it changed everything. The core idea is just beautifully simple. Instead of trying to build one super-duper fast processor, chip makers started putting multiple processors, or cores, which are like independent little brains, onto a single chip. It was a huge shift from a solo genius to a whole collaborative team.
To really wrap your head around how this works, let's use a great little analogy. Okay, imagine you've got 5 teaching assistants and 100 papers to grade. How do you get it done the fastest?
Well, they could split up the tasks, right? You grade question 1 on all the papers, I'll grade question 2. Or they could split up the data. Each TA just takes a stack of 20 papers and grades the whole thing. Both of these are forms of parallel work, they're just organized a little differently.
So let's see what that looks like in the computing world. Say you need to add up 24 numbers. You don't do it one by one in a long line. No, you give 3 numbers to each of your 8 cores. They all add their little piles at the exact same time. Then you just have to combine their 8 results.
And this diagram here illustrates the final, really elegant part of the process. Instead of one core collecting 7 different answers one by one, the cores team up. They pair off and add their results together in stages. As you can see, in just 3 quick steps, 8 separate results become one final total. It's smart, it's efficient, and it is so much faster.
So how are these digital teams actually built into the hardware? Turns out there are 2 main blueprints for getting all these cores to work together.
On the one hand, you have shared memory. You can think of this like a whole team working around a single giant whiteboard. It's really fast for collaboration, but yeah, it can get crowded. On the other hand, you've got distributed memory. That's more like each team member has their own private notebook, and they send messages to share information. It scales up much better, but all that coordination takes a bit more effort.
So where has this whole idea of digital teamwork taken us? The results are, well, they're just mind-boggling. Let's take a look at the absolute titans of the computing world today.
Just take a look at these numbers for a second. We're not talking about 2 or 4 or even 8 cores anymore. The top supercomputers in the world have millions of them. This isn't just a team,
It's a whole digital city of workers all focused on one single problem.
The number one system, El Capitan, has over 11 million cores. To put that into perspective, that's like taking the power of nearly 1.5 million high-end laptops and fusing it all into a single machine. That is the power of parallel computing at its most extreme.
So we hit a physical wall, a barrier of heat and power that completely stopped our quest for individual speed. But we overcame it. Not with a faster sprinter, but by creating an army of collaborators. It really makes you wonder, with these millions of digital minds all working together in perfect concert, what currently unsolvable problem are they going to conquer next?